Hello and welcome to lesson 12.4. This is our introduction to series. So we've talked about sequences, we've talked about explicit and recursive formulas, and now we're building up to series. So we're going to talk about what a series is, how it's related to sequences, and all that business. And just so you know, series is a major topic in calculus. I mean major. Especially, if you take BC Calc, that second semester, towards the end, is notorious for something called power series. Something that many students struggle with. You'll hear from a lot of engineers and computer scientists and stuff. Oh boy, I really liked calculus, but power series, it was tough. I actually love power series personally, but hey, I kind of love everything in math, right? And I say that all the time. So anyway, this is our intro to series, and we're just going to talk about what this is, how to add them up and evaluate them, and some of the properties that they follow. So you can read along here. Definition, what is this thing? So a series is the indicated sum of the terms of a sequence. So what is that? Okay, what does that mean, right? Well, suppose I had a sequence, right? I say, let's do the odd numbers, right? 1, 3, 5, 7, 9, and so forth, right? So this is a sequence of numbers. I've chosen the odd numbers. If I wanted to say the series of odd numbers, what that would mean is taking the sum of all those terms. So rather than having like commas between those, it'd be 1 plus 3 plus 5 plus 7 plus 9 plus ... right? And so it's just a, repeated sum, right? I'm adding all the terms of the sequence together. That's what a series is. And so depending on how many terms you're adding, a series can either be finite or it can be infinite. And then, I don't know, maybe that's the first time you've heard the word finite. If you're not sure, finite, well, if infinite, right? Infinite means not finite. And we have this idea of, infinity being never ending, right? Unlimited, kind of, right? Going towards infinity. Well, finite means it stops, right? Finite means it is, a particular set of values that's concrete, right? It has a stopping point. So, for instance, right, if I said the set of numbers 1, 3, 5, 7, and I put the set like this, that is a finite set because it only has 4 terms, right? The first term 1, second term 3, third term 5, fourth term 7. That's a finite sequence. Or sorry, that's finite. But you can also have infinite sequences, and that would be like if I had 1, 3, 5, 7, ... implying right, those ellipses, the ... implies it just goes on forever. So, yeah, okay. Now, if I have an infinite series and I only take the sum of part of it, that is called a partial sum because it's just a part of the sum, right? So maybe I have that 1 plus 3 plus 5 plus 7 plus ... but maybe I only add the first 3 together. That would be a partial sum because it's a part of the infinite sum of the odd numbers, but it's not the whole thing, okay? Partial sums are a really big thing you talk about in calculus. And then I just wanted to put the more formal definition here. The nth partial sum, and remember n refers to the index or term number, right? The nth partial sum of a series is the sum of the first n terms of that series. Will denote a partial sum, capital S sub n. Okay, that's usually S sub n is referring to a sum, a partial sum where n is a finite value. That's not to say you can't make it infinite, but yeah. Okay, so how do we write these things, right? How do you write repeated addition? Because how are you going to write 1 plus 3 plus 5 plus dot, 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 right? I mean, you can put the dot, 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 but what's a better way to maybe write that so I'm not just using this, vague, it just goes on forever business, right? So we express series using the Greek symbol, this thing, which we call sigma. So this symbol is called sigma, and all that means in Greek is sum. All right, so quite literally, that symbol sigma means sum. It means to add things together. And I'll zoom in a little bit here. This is sort of the general notation for a sum, for a series, right? So here's what we have, right? S sub n, maybe I'll do this in yellow here. S sub n, this is the nth partial sum. Unless it goes to infinity, of course, because you could make n infinity. I equals 1. So I, that's your index. And this one starts at 1. So the first term. Now the thing about a series is you can start it at any term you want. I don't have to add, 1 plus 3 plus 5 plus 7. I could just start at 5. And I could say 5 plus 7 plus 9 plus 11 and so forth, right? I don't actually have to include the 1 plus 3 if I don't want to, yeah? So depending, the I just tells you where the series starts. Usually we start at the beginning, right? But not always, not always. And we will manipulate the index in some cases. The number on top, this n, tells you where it stops, okay? So this is just the nth term. And you can think of this as the stopping point, right? So it's not going to go past n. So, if it says, if I have like a sigma of I equals 1 to 5, that means I start at the first term, a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. And it stops there. It doesn't go past it. It doesn't go to 6 and blah, blah, blah. And by the way, those should all be plus signs because it's adding, right? It's a series. And finally, the thing that you see here, a sub n is the sequence. Whatever sequence you're talking about. So often this is an explicit formula. Explicit formula. So, if I have an explicit formula for that sequence a sub n, I'll replace that a sub n with that formula because then I can actually carry out the calculation. Okay? So that's what all those pieces mean. Okay. And I know that's kind of maybe intimidating right now, but you use these enough, you'll be like, oh, no problem. I get what this is saying. So in the expression above, as I just said in yellow here, I is called the index. And that tells you the term position. Or I should maybe say, tells you, I'll say like which term. Which term the series starts at. My English teachers are probably yelling at me saying, did you just end a sentence on a preposition, Mr. Spake? Yeah, sorry, I don't know how else to phrase this. You say starts at what, right? You're preparing to say, right? If you didn't know what a preposition was, right? Preposition. When you're writing formal essays, all of a sudden we switch to English literature, right? Don't end on a preposition if you're writing like an essay or something because you don't want to see how this ends, right? As starts at. Well, you're kind of like starts at where, right? If I just look at that alone, starts at, you say, starts at, where? That's a preposition because starts at means you're preparing to say where it starts at. Yeah? Okay. Anyway, I don't know how else to phrase this, and that's just my quick little English lesson. And I hope I was right about that, so I'd hate to be spreading misinformation about that. Yikes. Someone fact check me on that. Say, hold me accountable. Mr. Spake, can't do that. All right. Example 1, compute the sum. So let's compute this guy, right? So the index I starts at 1, and you can see I have a explicit formula here. So what your sequence is, right? Your sequence is a sub I equals 5i minus 3, where I is, the starting position. It starts at 1. Personally, and this is just a quick note, that index I doesn't always have to be I. It's very common for your sequences. You can say I equals. Some people say N equals. Some people say K equals. Some people say T equals. I think those are the 4 most common to use for an index. Of course, you can use anything, right? Any letter is really fine. A lot of Algebra 2, like beginner sequence textbooks and stuff like that, use I. I, as in Mr. Spake, I don't quite really like this often because when I see 5i minus 3, I think that means 5 square root negative 1 minus 3, and I'm not the biggest fan of that. I'd rather write something like 5k minus 3 or 5n minus 3, personally. But it is very common to use I like this. And I don't want you to get that confused with square root of negative 1, because true, I is the square root of negative 1, but operating from this context, that's not what this means, okay? I'm sorry if that's kind of confusing. Math, much like any language, operates within a context, right? Okay, so let's compute this sum. Well, what does this mean, right? Well, it starts at 1, so I might write this, right? Starts at a sub 1, adds up to a sub 4. So what this is going to do is it's going to be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. Okay? Because it starts at 1 and then it goes to 4. Now, I have to know what those terms of the sequence are, where the sequence is given by 5i minus 3. So I got to find some space here. Maybe I'll just write it in blue so it doesn't clash too much. A sub 1, right? What is that? Here, you know what? I'd actually rather prefer to do below. I know this isn't the best video practice, but I don't care. All right. What did I say? A sub 1. What is that? Right? What is the first term? Well, it's 5 times 1 minus 3. And, of course, that is 2. So then what is a sub 2? It's 5 times 2 minus 3. That's 10 minus 3. That is 7. What is a sub 3? A sub 3 is 5 times 3 minus 3. That's 12. And finally, a sub 4, that's 5 times 4 minus 3. That's 17. Yeah? By the way, I don't need you to write all those. You can do that pretty much in your head, but I wanted to show you explicitly where I came up with those numbers. So then this is adding 2 plus 7 plus 12 plus 17. And then you just add those together. So 2 plus 7 is 9. 9 plus 12 is 21. So I'll just write that. 21 plus 17, that's 38. And there you have it. That's the sum, okay? So this series, if you add up all the terms, computes to 38. And that's all we're really doing, is computing these sums. Okay. Now, on to summation properties. So I can't remember enough about my own Algebra 2 experience regarding sequences and series. I can't remember how far in depth we went. And I haven't seen, in some of the textbooks I've seen, I haven't seen them actually talk about these properties. But gosh darn it, if I don't want to show you them. Because I don't think they're really that hard to understand. So I'm going to label these 1, 2, 3, 4. So this is going to be property 1, this is property 2, property 3, property 4. And, there might be some more properties, but these are the 4 I wanted to show you. And I just want to explain for a second what they mean. So property 1, right? The sum from I equals 1 to n of c equals cn. So what this means is it's implied that c is a constant, all right? Meaning it's a number. It has a value, right? Technically it doesn't need to be a number. You can just say it's a constant c that doesn't change, but often you might see this as a number. So example, and I am going to erase this, but let's say I sum from I equals 1 to 3 of a constant 10, okay? So what does this mean? Well, the sequence in question is just 10. It's a constant. It's 10. So a sub 1 equals 10. A sub 2 equals 10. A sub 3 equals 10. It doesn't change. It's constant, right? So the series is 10 plus 10 plus 10, which we know that that's 30, right? But ask yourself, how many times are you adding 10, right? You're doing 10, the constant, times 3. And hey, what do you know? The term you were adding up to was the third term. So this 3 is corresponding with that stopping point. And so that's basically what this rule says. It's just c times however many terms you're adding up, because it's just a constant term. The notation might look a little confusing, but intuitively, I think you practice enough with it, you say, oh yeah, that makes sense. I get that. Okay, next one. So it says the sum of c times a sub I equals c times the sum of a sub I. So basically what this means, and there is a kind of a reason we don't show you this till usually about calculus, because you might understand why this rule works a little bit more once you're in calculus. But maybe think of it like this, right? So suppose I have the sum of 3 times, I'm going to define a sub I to be 2n minus 1. Right, and I'll say like I equals 1 to 3 again, because I just want to do 3 terms. So what is a sub 1? Well, a sub 1 is 3 times, that's 2 times 1 minus 1, that's 1. A sub 2 is 3 times, 2 times 2 is 4, minus 1 is 3. And a sub 3 is 3 times, 2 times 3 is 6, minus 1 is 5. So if I add these things together, it's 3 times 1 plus 3 times 3 plus 3 times 5. And, you can calculate these, right? You can say that's 3 plus 9 plus 15. What is that? 18 is 27, right? Or you can notice that 3 is a common factor. So you factored 3 out, and then it's 1 plus 3 plus 5. But you see, 1 plus 3 plus 5, that's just the sum of the 2n minus 1 piece, right? So this is your 3 up here. This is I equals 1. If you were to just sum the odd numbers, 2n minus 1, 1 plus 3 plus 5, then the constant 3 is on the outside like this. So this is just a nice, easy property to use. If you have a constant multiplier, you can kind of factor that out of the series, because that factor is going to be part of every term in the series. So think of it as that's a greatest common factor, right? Or maybe not the greatest common factor, but it is a factor of every term in the series, which means you can factor it out. Okay? And so maybe I'll write that down. Says you can factor out a constant multiplier. That's what that means. Okay. The next two, I don't want to spend as much time. This rule, basically, so if you have two sequences added together, or really just, if it's like a polynomial or something, you can separate those into two separate series. So an example of this might be like, I'm just going to stick with that 2n minus 1 example, right? Let's say I go to 3, I equals 1. So what this means is you can view 2n as its own series, a sub I, and you can view the constant negative 1 as its own series, b sub I. And so because you're just adding these things, you can separate the first one as 2n plus the second one is just negative 1. And of course, they have all the same information about where the index is and where the ending point is, but you can just sort of split it up like this because it's just addition, right? And because addition is commutative, meaning you can add in any order, I can just do that, and it's not a big deal. And then this last one, I put this rule here because I wanted to, but if you don't get this right now, it's okay. It basically just means you can split up a series in any way you like. So let's say I have the series, of a sub I where I equals 1 to 10, right? That means you are adding a1 plus a2 plus a3 plus a4 plus ... to a sub 10, right? Well, you can split that up. You could say that this is the sum of a sub I from I equals 1 to 4 plus a sub I where I equals 5 to 10. And you might say, well, why does this work, right? Well, the first sum I wrote there is the index I from 1 to 4. So it's a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. That's that term. Plus, but then this other series just starts at 5. So it's a sub 5 plus ... up to a sub 10, which this whole thing is essentially equal to this. Now, I don't think we're even going to use this property today, but I just wanted to show you that it's here. Okay, maybe when you encounter this in pre-cal or calculus or wherever you go, you'll remember and say, oh, yeah, that makes sense. I can split it up. Okay. So let's do example 2, all right? And the thing about example 2 is you have the sequence, right? A sub n equals, or maybe a sub I, right? Is the 1/6 I squared plus 5I minus 10. That is the sequence. And if you just want to plug in a sub 0, a sub 1, a sub 2, a sub 3, a sub 4, if you just want to plug in 0, and then 1 squared, and then 2 squared, and then 3 squared, and then 4 squared, right? You can do that, and you can compute all of these. And that's fine. That's acceptable. But it's usually more often, a little bit easier to actually compute this by hand if you use the properties we have above. So here's what I'm going to do. First thing I notice is, I have a trinomial here, right? 3 terms, 1, 2, 3, all separated by the addition or subtraction sign. So using rule 1, so I'm going to say using rule number, sorry, not rule number 1, rule number 3, right? That rule number 3 says I can split this up. If I have plus, I can split them up as separate series. And so I'm going to do that using rule number 3. I'm going to say that this sum from I equals 0 to 4 of 1/6 I squared plus 5I minus 10. And by the way, this is a lot of writing. And I'm going to warn you, don't get lazy with writing this summation. You need to get in the practice of always writing that. That's something my teacher really emphasized on me, and it has saved my butt. You need to write that summation, okay? As exhausting as it can be. So I'm going to split this up into 3 separate series. I equals 0 to 4 of the first term, 1/6 I squared, plus, and this is where it becomes exhausting because you got to write the sigma symbol every single time for every separate series, 5I. And then minus, and you might say, well, is it different for minus? Well, no, because it's plus negative, right? Same thing. Sum of 10. So this is I equals 0 to 4, like so. So that's using rule 3. I've split this up into 3 different series. Now what can I do? Well, I notice that I have a constant multiplier here and a constant multiplier here. So I can factor out those constant multipliers, okay? So then, and that's rule 2. So using rule number 2, we find that the first term, right, we find that this implies 1/6 times sigma of I equals 0 to 4 of I squared plus 5 times sigma of I, right? That's really not how you should say that out loud. You should say 5 times the sum from I equals 0 to 4 of I. That's a mouthful. Minus this one. We didn't actually touch this one. And that's I equals 0. I say, oh my gosh, this is exhausting. I say, I know, I know what you're doing. I know what you're feeling. But from here, you can actually compute these pretty easily now, because what you've done is you've really simplified what sequence you're adding up here. I squared from 0 to 4, that's so easy. I from 0 to 4, easy. Adding up this, plugging in 0, 1, 2, 3, 4 for this whole expression, that's actually kind of a lot of work. And I don't want to do that, especially because there's a nasty fraction there, yeah? So we go to the next line. So this is 1/6 times, and I actually like to do brackets sometimes, brackets, parentheses, whatever, I squared from I equals 0 to 4. So it means 0 squared, which is 0, plus 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9, plus 4 squared, which is 16. So that's the first one. Then plus 5, right, my constant multiplier 5, times, and now I need to compute this sum. And it's from I equals 0 to 4, so I equals 0, plus I is 1, plus I equals 2, plus I equals 3, plus I equals 4. Boom. And then notice that last one, minus, well, actually, if you come back up here, you see 10 is a constant. So we can use this rule, rule number 1, to evaluate that piece. Because what does this mean? It means I'm doing 10 4 times, right? This from I equals 0, 10. That just means 10 plus 10 plus 10 plus 10. But if you use rule number 1, you can just write that as 10 times 4, which is a heck of a lot easier, especially if, the term on top went really big. And so this was using rule number 1. Using rule number 1. And now you can add up all these things together. So this is 1/6 times 1 plus 4 is 5, plus 9 is 14, plus 6 is 30, plus 5 times 0 plus 1 plus 2 plus 3, so that's 3, 6, 10, minus 10 times 4, that's 40, right? And then this just becomes, 1/6 times 30 is 5, and 5 times 10 is 50, and then that's minus 40. So I should get, hold on. Ooh, actually, hold on a second, everybody. Hold on a second. I think I messed up somewhere. Yeah, okay, hold on. Red flag. Red flag. Red flag. Uh-oh, he's not good for you. Red flag. Something happened. I made a mistake. This rule up here starts at 1. But down here, I didn't start at 1, I started at 0. Think about that. It's a sub 0 plus a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. How many terms is that? 1, 2, 3, 4, 5. So it's actually not 10 times 4. It's 10 times 5. Yeah, that's it. Oops. I probably should have started this at 1 so it didn't get confusing like that. But oh well, live and learn, right? Okay, so I'm actually glad I made that mistake because it's a super common mistake you could make. And so I got 5 plus 50 minus 50 equals 5. And that's it. That's the summation. Ta-da! Hooray! Okay. And there it is. And to be honest, I feel like that's enough for a video, but nah. We're gonna go here. Okay. So that's basically the lesson, right? This is what I'm teaching in class, all that business. And then for you guys, these are the practice problems you're doing in class. I'm going to go ahead and do the practice problems here, and I will just keep a watchful eye on you that you are not watching this video or blah, 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 to do these not honestly. Okay. So you can approach these one of two ways. One, you can just compute every term of the series and then add them all up together. Or you can use the properties of summation to make your life a little bit easier. I'm going to do it with the properties of summation because I want you to see some examples of them in action. But I want you to know you don't have to always use them, okay? For example, number 1, you may be very able to quickly identify that the sequence you're adding up is 7 plus 9 plus 11 plus 13 plus 15. How many times am I doing this? 6 plus 17. Okay, because that's what it is. And that's honestly, guys, that's good enough. It's fine. I'm good with that if you want to write it that way. I am just, this part of the video, I just want to show you how those properties can be used. It is 100% A-okay if you don't want to use them today, okay? You're beginner students learning how to use these things. You will master these in calculus, okay? So anyway, I'm going to use the properties here. So I'm going to use two properties in one. The first property says I can split them up because it's plus, and then the other property says I can factor out 2 from the other expression. So this will be 2 sigma I equals 0 to 5 of I plus sigma I equals 0 to 5 of 7. And this is using both rules, rules 3 and 2, okay? So that's using both of those rules. And now I can see very clearly that this is 2 times 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus, think about it as what's the distance between these two, right? From 0 to 5, 1, 2, 3, 4, 5, right? How many terms are there? 1, 2, 3, 4, 5, 6. So kind of like our last problem, it's 7 times 6. I'm adding 7 6 times. And so this becomes 2 times, let's see, 1 plus 2 is 3, plus 3 is 6, 10, 15. Plus 7 times 6, well, that's 42. So that's 30 plus 42, which is 72. Okay? Done. And the reason I did it this way is, remember, I mean, I did write 7 plus 9 plus blah, blah, blah. But if I don't have a calculator, that's a lot of numbers to add. Don't you think? I mean, I don't know. Maybe you can add that in your head if you're really, really great at arithmetic. I don't want to do that. I actually think that using the summation property is a lot easier when you don't have a calculator. You might say, well, why can't I just use a calculator? Well, I'll tell you, a calculator can already do this. So there's not really a point, unless you, whatever. Okay, so let's do the next one. Equals 3 times sigma 1 over k. You say, whoa, my God, Mr. Spake, you're moving too fast. What are you doing? I said, again, I used that rule because, and I'm going to write this up here. 3 over k is 3 times 1 over k. So you can use that rule of factoring out the constant, right? 3 is the constant. I factor that out of the series. And then I just have 3 times 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And I do need to add that. And I'm going to do it without a calculator. So 1 plus 1/2 is 1.5 plus 1/3 plus 0.25, right? So really, that's just 3 times 1.75 plus 1/3. And then if I distribute that in, that's 3 times, 1.75, 8/4 is 2, so that's 7/4 plus 3 times 1/3. So now that's 21 over 4 plus 1, which equals 25 over 4. That is not what I wanted. I did not want an ellipse because we are done with conics. I'm not talking about conics. Equals 25 over 4 rectangle. Nice. Okay. Nice. I converted those to decimals because I didn't want to do fourths. I don't know. Whatever. That was just me reasoning it out. Okay? Okay. Beautiful. Nice. Let's move to the next one. Number 3. Okay. So we just want to do this one. So I can factor out the 5 here because that's a constant. So times, I don't like the sigma I drew. If I hold this, will it do it? Ooh, that's not bad, but it's not very natural. I'll just do this. 2 to the k minus 1. This is k equals 3 to 5. So, see, if a sub n, or rather a sub k, right? If a sub k equals 2 to the k minus 1, then a sub 3 is 2 to the 3 minus 1. That's 2 squared, which equals 4. And a sub 4 is 2 to the 4 minus 1. That's 2 cubed equals 8. And then a sub 5 is 2 to the 5 minus 1, which is 2 to the 4, which is 16. So really, this equals, here I'm going to put this here, equals 5 times, let me parentheses, e, parentheses, 4 plus 8 plus 16. And let's see, that's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So 4 times 7 is 28. That should be 140, I think. Yeah. Is that right? I'm gonna actually check my key here. Yes, I'm good. Just making sure during the video. Okay? And that's that process. There's some other stuff you could do here. You can play with the exponents if you like, but I'm not going to do that in this video. All right. Next one. And this one's actually a really interesting one. This is one I'm excited to see you guys really grapple with in class. How the heck do I add this? Okay. So your sequence here is interesting. It's got two pieces. -1 to the t and x to the t. And you might be thinking, could I factor out -1 and then it's x to the t? Well, no, because it's x, -1 to the t, that's exponential, right? It's being exponentiated, and t is changing, so I can't factor that out. So what does this look like? Well, if a sub t equals -1 to the t times x to the t, then what is a sub 1? Well, that's -1 to the, a sub 0, right? Because that's where we're starting. That's -1 to the 0 times x to the 0. Well, -1 to the 0 is 1, and x to the 0 is also 1, so that's 1 times 1 is 1. A sub 1 is -1 to the 1 times x to the 1. Well, x to the 1 is just x, and -1 to the 1 is negative, so that's negative x. Now then, see, a sub 2 is -1 squared times x squared. So -1 squared is positive 1, which means this is positive x squared. A sub 3 is -1 cubed times x cubed, and -1 cubed is negative x cubed. Are you starting to see a pattern? And then a sub 4 would be -1 to the 4, x to the 4. That's positive x to the 4. So what's happening to the signs here? Well, this one's positive, then negative, then positive, then negative, then positive. We call this an alternating series because it alternates between positive and negative every term. And it's defined by this -1 to the t. That's what creates the sign flipping. So if I do this from 0 to 7, I should get 1 minus x plus x squared minus x cubed plus x to the 4 minus x to the 5 plus x to the 6th minus x to the 7th. That's that series fully expanded. I can't add any of that together because they're not numbers, so I just leave it like that, and I'm done. Finished. Okay. 2 more problems. Okay. Write each sum using sigma notation. You do not need to evaluate the sum. Cool. So let's look at this first sequence here, number 4. 1 plus 3 plus 5 plus 7 plus 9. So what you need to do, right, is you need to figure out, because I'm writing a series of a sub I, where I presumably starts at 1. You can start it at anywhere you like, but we'll just start it at 1, and it goes up to some value n. So this is a sub 1, this is a sub 2, 3, 4, and 5. So I do know that this top number on the above the sigma is 5. But what is the series, right? Or what is the sequence that generates this? Well, this is where you have to get that explicit formula, yeah? Notice that this is plus 2 every time. So this is an arithmetic sequence, which if you recall, we have a rule, we have a rule for that. So how do I find the explicit formula for arithmetic sequence? I'm going to write it out because it's bothering me. Well, a sub I equals the first term a sub 1 plus I minus 1 times d, where d is the common difference. So in this case, a sub I equals a1. What's the a1? Well, it's the first term 1 plus, and I see this is I minus 1 times the common difference, d is 2. Now I can clean this up a little bit, distribute the 2, I get 2i minus 2 plus 1 is minus 1. So that's what a sub I is. So the sequence I'm going to write, that's my sigma. I equals 1, that's where I start. And now I'm adding up to the 5th term. And the sequence is 2i minus 1. So you have to find the explicit formula, and then you can create your series like that. Okay, and then I'm doing one more, and then that's pretty much it for the video. Okay, so how do I create a series for this? And notice it says you don't have to evaluate. Well, here's a few things I notice. First thing, a sub 1 is 1. A sub 2 is 4, that's 2 squared. A sub 3, that's 3 squared, right? 4 squared, 16. 5, 6. You should be seeing that square pattern. So it looks like, right? Looks like index, whatever that index is, not to the power of 6, squared, right? That's what's getting that number. Also, it is alternating plus, minus, plus, minus, right? So how do you deal with a plus, minus like this? Well, remember this guy? This, the -1 to some power, that's what helps create it alternate. So what you're going to want is a -1 to some power, we'll call it k. All right? And then finally, adds to infinity because of this ... right? This ... means you don't stop. So, sigma, right? Sigma. Where does the series start? Sorry, I equals 1, or rather, you know what? Today I'm going to do k. I'm going to say k equals 1, because you can choose whatever letter, up to how long am I doing this? Forever. This is an infinite series because it doesn't stop. So from k equals 1 to infinity of, well, the -1 to the k, that's what's helping it alternate. However, However, if you start it here, what's negative 1 to the 1? It's negative. So you need to handle this somehow, right? Because see, negative 1 to the 2 is positive. And that doesn't match these signs because the first term needs to be positive and the second term needs to be negative. So how do we deal with that? Well, any way you like. One thing you could do is you could change the index so that it doesn't start at 1, so it starts at 0 or that it starts at 2. What I might say is if you do negative 1 to the 1 plus 1, right? Or maybe even minus 1. Plus 1 or minus 1 works. I'll do minus 1. Okay, 1 minus 1, then that's positive. 2 minus 1 gets you negative. So I'm going to write k minus 1 up here. And really, you have a lot of choice here. You can say k minus 1. You can say k plus 1. You can say whatever, right? Whatever makes it start on a positive number. And then, excuse me, I'm doing the index squared, right? And the index in question is k. So it's times k is the index that's getting squared. And so that's my infinite series. That one's kind of hard, low-key. I mean, for a first-timer, this is your first time with series of sequences? Yeah. That was kind of difficult. But, yeah. You get good at this now, you're going to be a master in calculus, just so you know. Going to be a master. Okay, that's pretty much it for the lesson. I mean, that's the lesson and the practice problems all worked out. I do have some stuff down here, but I'm not doing that in this video. 2 reasons. This first one is a think about it question. I genuinely want you to think about that, and I don't want anybody cheesing it. How do you compute this sum? Notice it's from k equals 1 to 100. How do you do 1 plus 2 plus 3 plus 4 plus ... up to 100? And how do you do that by hand without a calculator and not, exhausting yourself actually adding all that up, okay? So think of a creative way to add that together. And I doubt we'll actually have time with this on the day we do this, but the activity is you can derive, this right here will tell you the sum, the partial sum of any arithmetic series, and I want you guys to prove that. But, if that doesn't happen today, it's fine, it's whatever. But these aren't things I'm going to show in the video, so thanks for sticking around. This one was kind of long. That's why we're doing it in class. And yeah, have a good one, and I'll see you later.